your own reference. Okay, if you look at chapter 3, we have been talking about statics, fluid statics. Now, chapter 4 talks about what, guys? Fluid kinematics. Do you know what the word of kinematics means? Can someone tell me what
the energy in movement?
Movement. Kinematics means movement. So we are basically moving forward to look at a fluid in movement. And this chapter and the rest of the other chapters gives us the fundamentals, some equations to analyze a fluid in motion. That is what it means, right? Chapter 4 is an introductory, and it starts with what? A very interesting picture of a hurricane. Our main objectives, guys, there are 5 points. The first one is to understand the role of material derivatives in transforming between Lagrangian and Eulerian descriptors. We will talk about it. Point 2, distinguish between various types of flow visualization. Point 3, appreciate the many ways that fluid move and deform. And then point 4, distinguish between rotational and irrotational regions of flow. The point number 5, Reynolds transform theorem, is the point for reading. We will not discuss it. But let me just stop a little bit here in the objectives, because it's not clear to you. I don't think it is clear to you. What is Lagrangian and Eulerian? Let me tell you something, gentlemen. Fluid studies are mainly based on experimental EXP or computational COMP. In other words, gentlemen, if you want to analyze a problem related to a fluid mechanics, you have 2 approaches. There is no a third one. Either to build an experimental test rig and run an experiment and then comment on the behavior of the fluid. That is one very conventional way. The other way is to build a computational model. Go to mathematics and then try to formulate the problem at hand and put it in an exam in a mathematical model, and then solve the mathematical model. It will give you an answer, right? So there are 2 ways. Either look at it from experimental point of view or from computational point of view. Experimental, usually it shows you, you can visualize, you can look at the patterns of the flow. Okay? When you run an experiment, you can visualize the flow, right? And look at patterns of the flow, as well as exporting data. And this is this point, guys. Distinguish between various types of flow visualizations. Okay? Computational also give you data. You can also visualize it using what? Graphs and so on. Okay? But computational is different from experimental, because experimental is physical, computational is just theoretical. That is one point. Now, whether it is experimental or computational, gentlemen, looking at fluid flow, there are 2 main schools of thought. Okay? Now, if you have a pipeline, let us say this is a pipeline, okay? And the fluid goes from here and leaves from here. Okay? What I mean by schools of thought is that some people look at this fluid as particle moving. You know what I mean by particle? Small particle movings. Right? Some people say the best way to analyze a fluid flow in a domain is to look at it as particles. Right. The question that comes here, for example, this is a simple pipe. How many particles do I need? 1,000, 2,000, 1 million, 3 billions, trillion. The fact is that, guys, if you look at a fluid flow from particle point of view, you need a huge number of particles in order to represent the flow. Now, this is school of thought which basically look at a fluid flow as a combination of huge number of particles called Lagrangian. It's called what, guys? Lagrangian. So Lagrangian school basically look at a fluid flow as a combination of a huge number of particles, and then it seeks to what? To follow the path of the particle until it goes. And the path of the particle basically gives an idea about the nature of the flow. Some people said, no, 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 no. This Lagrangian approach, which basically visualize or conceives the flow as a huge number of particles, is not realistic, because how can we, statistically, it is difficult to follow a huge number of particles. They said no, rather than a particle, they will look at ensembles. Ensembles means what? Talk about small computational domain. Do you see my in my drawing? A finite volume, yes. Right? Rather than looking at a particle, okay, look at what? A small finite volume like this. And then study the movement of flow within the finite volume. And then integrate all over the computational domain to give you a whole picture of what is happening. This is another school of thought. And these people who follow this school of thought are called what, guys? Eulerian. Eulerian. So Lagrangian and Eulerian basically are the two main schools of thoughts that basically study the fluid motion. Okay, both of them are, by the way, if you go to masters in fluid mechanics, you might find both of them are used. I will tell you why. In any conventional fluid flow, Eulerian is used, but there are some applications. For example, there are some applications like what, guys? You know, your cars, there is fuel injectors, right? Most of the cars now, they have what? Fuel injectors. And these injectors basically inject the flow in a very tiny particle. Do you agree with me?
قصدك على البخاخات دكتور؟
ها؟
زي البخاخات حقت
البخاخات الله يخليك.
ايه.
Injectors هي البخاخات. The injectors of the fluid in the car basically sprays the fuel, whether it is diesel or what, or petrol. Now it sprays the fuel in a very small particle. This application in particular is very prone to Lagrangian approach. Lagrangian approach is better because you can say, okay, 1 million particle is enough. 1 million particle is enough to model the spray combustion, right? But if you have a domain like this, a pipeline, it is difficult to use Lagrangian, and therefore Eulerian is important. So gentlemen, this is briefly fluid mechanics. Fluid mechanics, if you want to study fluid dynamics, that is to say a fluid in movement, you can either go to experiment or computational. Both of them will give you data, right? There are two schools of thought, Lagrangian and Eulerians. You can follow each one, whatever you want. But mostly Eulerian, Lagrangian is useful where there is, you know, particles. You can model the flow with the particles, like spray combustion, right? Although Eulerian also is used, but Lagrangian is more suitable, okay? So these are the 4 points. We will go through this chapter very fast. It is not a big chapter. Lagrangian and Eulerian descriptors, we have just talked about them, right? And this is the brief definition of them. There are two distinct ways to describe motion, Lagrangian and Eulerian. Lagrangian description to follow the path of individual objects, particles. Okay? The method requires use to track the position and velocity of each individual fluid particle and take to be a partial of fluid identity. So that one represents the fluid. This is Lagrangian. Okay? The Eulerian is different. A more common method is Eulerian description of fluid motion. The Eulerian description of fluid motion, what? Finite volume called a flow domain. That as I talked to you, okay? Or a control volume is identified through which fluid flows in and out. Okay? Now, instead of tracking individual fluid particles, we defined field variables. We define what? Field variables, function of space and time within the control volume. Let me just stop here, gentlemen. Okay? And let me just go back again to this fluid domain, this pipeline. Okay? You may agree this pipeline, it has 3 dimensions, right? X, Y, and what, guys? And Z, صح?
Yes.
There is a 4th dimension. What is it, guys?
Time.
Time. Right? Now, when we talk about field variables, gentlemen, we talk about the main variable that control this flow. We have the pressure, we have the velocity, we have the acceleration, we have the energy as well. When you go to masters, you will talk about energy. Now, if you look at the pressure, if you agree with me, if you talk about the pressure inside this pipeline, the pressure is function of both X, Y, Z, and what, guys? And the time. Similarly, the velocity. Similarly, what? The acceleration of the fluid flow. Do you agree with me? Or there is an ambiguity here? Okay? So it consists any variable inside the flow you consider, make no mistake about it. It is 4-dimensional. It is function of X, Y, Z, and the time T, right? Therefore, if you look carefully, the velocity itself at any point here, talk about this point, we wanted to define the velocity. The velocity has 3 components. Along the X, and it is called U, along the Y, and it is called V, and along the W, and along the Z direction, and it is called what, guys? W. I think you have this. Now, the velocity is 3-dimensional, and make no mistake about it, each one of these components is also 4-dimensional, which basically gives the fact that the total velocity is 4-dimensional. So U, the x-axis velocity, is a function of x, y, z, and t. I is a unit vector, which indicates that this is the velocity along the x-axis. V is the velocity along the y-axis, indicated by g, the velocity vector, is also a function of x, y, z, and t, and similarly w. Now, this brings a lot of complication, gentlemen, to your understanding of a fluid flow. Velocity, pressure, and acceleration are quite complex. And we will start with the velocity. The velocity is 3-dimensional. It's 4-dimensional in reality, but it has 3 components, u, v, and w, along the x, y, and z respectively. Each one of these components is a function of x, y, and z, and the time t, right? So while there are many occasions in which the Lagrangian description is useful, the Eulerian descriptor is often more convenient. As I said, this is when you compare Eulerian and Lagrangian approach. Eulerian is more convenient because it is easy to analyze, right? Experimental techniques, experimental measurements are generally more suited to Eulerian descriptions. Okay, so the Eulerian we consider a control volume. We don't consider a particle. We consider a control volume, and then at some points within this control volume, we look at the variables velocity, pressure, energy, whatever it is, temperature, species concentration, whatever it is, we look at it as four-dimensional function of x, y, z, and t. Here he is giving you a very simple example. He said a steady, incompressible. Now, when we come to steady, do you remember chapter 1, guys? When we talk steady about a steady and unsteady, what are we talking about? Huh?
When we talked about what,
about
Doctor?
huh?
When we talked about what, قطع.
Steady and unsteady flow. What is the difference?
It depends on the viscosity in the relay.
لا. Now,
steady.
I think the velocity, Doctor. The difference in the velocity.
What?
The velocity.
Steady flow means what? And unsteady means what?
Steady means change with the time, Doctor.
Aywa. Steady means do not change with the time. Unsteady means changes with the time. Now, let's look here. The velocity v is two-dimensional. Two-dimensional. And we talked about the flow is two-dimensional, one-dimensional, and three-dimensional. صح ولا ما صح? Do you remember? Chapter 1, classification of fluid flows. We have steady, unsteady. We have one-dimensional, two-dimensional, and three-dimensional. This is a two-dimensional. He said a steady means doesn't change with time. Look at this expression. Do you see the time here? Do you see time here?
No.
No. So that is an indication to the fact that the flow is what, guys? Steady. Now, is it IJK or only IJ?
IJ.
So the flow is what, guys? It's two-dimensional. It is only U and V. W is not there. Because basically here there is plus 0K, if you agree with me.
Yes.
So there is no velocity along the span wise, along the z direction. So the velocity is two-dimensional. It's steady because there is no time here. Right? There is no time mentioned. So that's the flow is steady. It's given by this expression. V, which is U and V, has two components only. U is given by what? 0.5 plus 0.8x. And V is given by what, guys? 1.5 minus 0.8y. Okay? Where x and y coordinates are in meters and the magnitude of the velocity are in meter per second. Stagnation point is defined as a point in the flow where the velocity is zero. That is the definition of a stagnation point. We have had it before. A, determine if there is any stagnation point in this flow, and if so, where? He's asking you this velocity field. Is there any stagnation point? If there is a stagnation point, where it is? B, sketch the velocity vectors at several locations in the domain. So basically, gentlemen, the issue is if there is a stagnation point, we can simply say the velocity is equal to what? Because this is the definition of a stagnation point. The velocity is what, guys? Is equal to zero. If there is a stagnation point, then we have to equate this velocity vector to zero. We have to equate u to zero and v to zero. Now, equating u to zero, guys, give us what? Give us x equal minus 0.65. Equating v to zero give us y 1.875. Do you agree with me?
Yes.
Do you agree with me, gentlemen? So that means indeed there is a stagnation point and it is positioned as what? It is positioned as what? Minus 0.65 and what? 1.875. Because If there is no stagnation point, we will not get an x and y values. But indeed, when we assume there is a stagnation point and we equate v to 0, we got stagnation point at these coordinates. Okay? So here at this coordinate, the velocity comes to 0. And then he's asking you to sketch. Okay? If you sketch it, if you can see that the stagnation point falls at where? At x equal minus 0.85 and y equal what?
1.8.
Yeah, 1.8. And then about this point, the vectors, you can see the vectors. The vectors move around it because here the velocity is equal to 0. So any velocity here comes to 0. So the velocity has to move away from it. Do you agree with me?
Yes.
Right? So this is a very simple example, a two-dimensional velocity profile. We determine the stagnation point. We said steady because there is no time mentioned here. Two-dimensional because the velocity along the z direction is assumed to be negligible or 0. Okay? Now we will come to the acceleration field. Okay, the acceleration. What is the acceleration relation to the velocity, gentlemen? Acceleration A is a derivative of the velocity, right? With
Yes.
respect to time, صح يا شباب?
Yes.
This is our definition, right? So we want, listen guys, I'm not going to ask you to drive here any relation. Okay, but I just want you to understand it. Now, if you remember, the Lagrangian approach, right? If you look at a particle, okay, the velocity at any time t of a particle is a function of what? Of its x component, y component, z component, and the time. If we look at the components, if we look at the components of the velocity, if you have a particle, if we look at a particle or a velocity here, okay, the velocity of this particle is a function of x, y, and what, guys? And z, as well as what, guys? As well as the time. صح ولا ما صح يا شباب?
Yes. Doctor,
Yep.
in the Lagrangian approach, we measure the velocity along the whole pipeline, the whole tube.
Along the 3 dimensions. Along the 3 dimensions, يا ما along the whole tube. And then you integrate. In the Lagrangian, you have to follow each particle alone, separately. In the Eulerian, you build an ensemble, small finite volume. Like that. And then you study the movement of flow in this finite volume, and then you integrate.
So, Doctor,
Okay.
here we can't use Lagrangian in any case because we will make 100 or 1,000 particles and do the same.
Not 100, not 1,000, guys. Yeah. You have to take millions, hundreds, few millions. In spray combustion alone, you have to use a few millions, like 10, 20 million particles, in order to get a good representation of the flow. That is why Lagrangian is very difficult. But the other one, no, you can divide into small volume or large volume. So it is doable. It is cheap. It's not expensive, the Eulerian approach. Let us stick to the, let us find an equation for the acceleration. We said the acceleration is basically what, guys? dv by dt, صح؟ يا شباب تابع معي. Do you remember when we derived the change of specific volume? We said rho is a function of what? Of T and P. Huh? Do you remember? The specific volume V is a function of what? Temperature and pressure. That is when we talked about the isothermal, the compression, coefficient of expansion, and coefficient of expression. Do you remember, ya shabab?
Yes.
How did we differentiate this del V by del V by del T? Del V is equal to what? Del V by del T dP plus del V by del P dt dP at constant temperature, صح? We said dV is equal what? Del V by del T at constant pressure dt plus what, guys? Plus del V by del P dP at constant temperature, صح? Do you remember this? Apply the same principle here. Apply the same principle. V is actually V of x, y, and z particle and the time t. So dV by dt, that is the acceleration, is equal to what? D by dV to all this. So it will become equal what? Del V by del T dt by dt, del V by del x dx by dt, plus del V by del y dy by dt, plus del V by del z dz by what? By dt. This is a simple differentiation to this equation, to this function here. V is a continuous function of its components, x, y, z, and the time t. If you want to get del V by del T, that is the total change. If you have to get del V by dV by dt, you have to use the four components existing here to get the whole expression. Now, if you look carefully, dx by dt, dy by dt, this is the distance divided by what, guys? By time. This gives you u, this gives you v, and this gives you what, guys? W. Am I right or wrong?
Yes.
The change of distance with respect to time is velocity. Therefore, if you look at the acceleration, it will become what? It will become del V by del T, dt by dt disappear. Do you agree with me? This one will disappear. So it become what? Del V by del T. So that is the main unsteady component of the velocity, plus u del V by del X, plus V del V by del Y, plus W del V by del Z. Right? This is, if you go back to your mathematics, this is a gradient, gentlemen. This is what? This is the gradient. Do you remember the grad, V del grad, dot, the dot product of a V and a gradient operator? Do you remember from your mathematics? Anyway, that doesn't matter. You have to go back to your mathematics and remember. But the acceleration is given by this components. Now we have to move further, gentlemen. Okay. This is the acceleration along the x. This is along the y, and this is along the z. Okay. Right. If you expand them, guys, you will get each components. If you expand this, for example, this one here, let's look at this, u del v by del x. Okay, u itself this u is a function of what, guys? This v is a function of x, y, and z and t. صح ولا ما صح يا شباب؟
Yes.
If you expand it, you will get this expression, gentlemen. I'm not gonna ask you to drive it, but if you go back and expand it, operate your differential, you will get three components for the acceleration: ax, ay, and az. In the exam, if I ask you to calculate the acceleration, this equation will be what, guys? Provided. If you look at it, it is easy to cram. Ax is what? This is the acceleration along the x. It is what? Delta u by delta t, that is the velocity along the, plus u del u by del x, plus v del u by del y, plus w del u by del z. You are always differentiating the x velocity u with respect to t, x, y, and z, and multiplying by the relevant component of velocity. Similarly, ay, del v by del t, plus u del v by del x, v del v by del y, w del v by del z. Az, w by del t, plus u del u by del x, plus v del u del w by del y, plus w del w by del z. This is an expression for the acceleration. And if in the exam, if in the midterm exam, I asked you to get an acceleration, usually you will have a velocity vector. This equation will be provided. Let us move forward, and we have an example. I think we have an example here. Now, basically, he wants to prove that this equation is valid, right? Look at this equation, if indeed is valid or not. Look at this example. The example says Nadine is washing her car using a nozzle similar to the one in the sketch. The nozzle is 9.91 centimeter long, the distance 9.91, with an inlet diameter 1.07 and an outlet diameter 0.46. Okay, the volume flow rate is given as 0.053 and the flow is steady. Estimate the magnitude of the acceleration of the fluid particle moving down the center of the nozzle. You want the acceleration. So we know the acceleration is the change of velocity, okay, with respect to what, guys? With respect to time. Okay, if you look at it carefully, he gave us the volume flow rate and he gave us the diameter here and the diameter here. So we can easily get V1, which is equal to what? V dot over A1, صح يا شباب? Similarly, we can get what? V2 is equal to what? V dot over what? Over A2, صح يا شباب ولا أنا غلطان؟ You can get the velocity because you have the volume flow rate and you have the area, the diameter. So you are given the diameter here and they are given the diameter at the outlet. So you can calculate V1 and V2 and what? And the acceleration is what? The acceleration will be what, guys? Will be delta U by delta T, صح ولا ما صح?
Yes.
Now, delta T, you can replace it by del X by U average. This is del X, صح? If you divide del X by U average, by the average velocity, you get basically delta T. The time the particle moves from here to here is equal this distance divided by the average velocity. The average velocity is what? Is equal to V1 plus V2 divided by what, guys? By 2. Therefore, the acceleration is equal delta U by delta T, and delta U is equal what? U out minus U in. Rather than delta T, we will put delta X divided by U average. U average is what? U in plus U out plus U in divided by 2. And if you raise it up, this becomes, you get this expression, Yashba. Are you in agreement with me? Are you in agreement with me, or there is something not clear to you?
Repeat your turn, please.
Again, the acceleration is what? Del U by delta T, صح? Change of velocity divided by the change in time, صح? Change in velocity is U out minus U in. Change in time, this is the time for the particle taken to cross the distance, what? From the inlet to the outlet, صح? The time is basically equal the distance divided by the velocity, صح ولا ما صح? Velocity is equal what, guys? Is equal distance divided by what? Time, صح? Therefore, the time is equal what? Is equal the distance divided by the velocity. The velocity is the average velocity, which is what? So rather than delta t, we will put delta x divided by u average. Delta x is what? Put it delta x as it is. U average is u out plus u in divided by 2. These two came here. Do you agree with me? It will come there. صح ولا ما صح?
Yes.
Now this takes this one up. It becomes 2 delta x divided by u out minus u in. Take them up. You will get a complete square difference.
Doctor,
Uh-huh.
why didn't we use the equations in the previous slide? We just
Well, just a minute. Well, we are coming. This is a conventional way. Okay? This is the conventional way. Are you happy with it?
Yes.
Okay. Now come to the equation. This gentleman said the equation. Okay? Where is ax? Here is ax, صح? We are looking to the acceleration along the x direction only. Take this equation, which is del u by del t. Del u by del t is equal to what, guys? Is equal to 0, صح ولا ما صح? We don't have a velocity v, we don't have a velocity w. So ax become what, guys? Do you agree with me?
Yes.
For the one which we have been talking about, for the example of the nozzle, the flow is one-dimensional. There is no velocity v, there is no velocity w. The flow is steady. So del u by del t will disappear. Del u by del y will disappear. Del u by del z disappear. There is no v. So only we have this component, u del u by del x. Now u, if you look at it, this u is u average, which is what? U in plus u out divided by 2. This is this u. Now del u by del x is what? Is u out minus u in divided by what? Delta x. Okay, now this is basically u out square minus u in square divided by 2 delta x. صح ولا ما صح?
Yes.
This is the same expression here. We reach to it here. Go here and you see, okay, everything is 0. So when he get the same expression, that means, ya shabab, that the acceleration equation we derived is absolutely valid. The acceleration ax is equal u out square minus u in square divided by 2 delta x. Substitute, you get what? Acceleration. The issue is he took it conventionally. He used a conventional way here. Okay, he used a conventional way here in order to tell you that the equation you have derived, right, is also valid, is also correct, whether you follow the conventional way, the simple mathematical way, or you follow the differential equation you have derived, will lead to the same results. Okay, that is what he wanted to tell you. Again, these slides talks about the same results we got. The acceleration is basically the dot product of the velocity and the gradient operator. Okay, the same, he's talking about the same issue here, right? Another example, guys. Another example, material acceleration of a steady velocity fluid. Consider the steady incompressible two-dimensional velocity field of example 4.1. Example 4.1 where is example 4.1 يا شباب? This is example 4.1 صح? This is the velocity field. The velocity is two-dimensional, u and v only. U is equal 0.5 plus 0.8x and v equal 1.5 minus 0.8. Okay, so what is he talking about? Let us come back to the slide. Calculate the material acceleration at point x equal 2 and y equal 3. Sketch the material acceleration vectors at the same array x and y values. So we have the velocity guys. صح ولا ما صح? U is equal to what guys? U is equal to what?
Del U by del T.
لا 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 لا. Just go to the velocity first. This is the velocity. This is the example. This is the original example. So U is equal to what guys? 0.5 plus 0.8x صح? And y is equal to what? And v is equal to what? 1.5 minus 0.8y. So u is equal to 0.5. Let me put it. U 0.5 plus 0.8x. U, where are we? U, yeah, it is like in where we went so far. What are we doing here? Okay, U is equal to what guys? 0.5 plus what? 0.8x. And v is equal to what? 1.5. This is v and this is u, صح? He wants the acceleration at this points, at this point, x equal, okay? Now, where is the acceleration, guys? Where is the acceleration? In the exam, if something comes to you like that, you will be provided the acceleration. Where is the acceleration field? So basically, we want to apply this equation here. Okay? Now, take it into your consideration. There is no AZ, right?
Yes.
We have only AX and AY, صح يا شباب?
Yes, that's right.
Okay? Now you have to apply this equation and this equation to the problem you have. Okay? So this is AX and this is AY. Now, do we have del U by del T is equal to 0, صح يا شباب?
Yes.
Now we have del U by del X. Remember U is equal to what? Put it this way here. 0.5 plus 0.8 x. Okay? And y, sorry, v is equal to what? 1.5 minus what? 0.8 y. Now come and apply the differentiation. Ax equal del u by del t. Del u by del t is equal to 0. U del u by del x. This is u. So del u by del x is valid. صح ولا ما صح يا شباب? It is equal to 0.8. صح? Now del u by del y. This is u. What is del u by del y? Zero. It is 0. Come here. We don't have w in the first place, but also del u by del z is equal to what, guys?
0.
Is equal to 0. So we only have u del u by del x. U is 0.5 plus 0.8x. He put it like that. And del u by del x is equal to 0.8. Do you notice? The rest are 0, 0, 0.
Doctor,
So that will become what?
This 0.4 plus 0.64x.
Yeah, exactly. multiply 0.8 دخل put
Yes,
huh?
yes, I get it.
Now
Yes.
come to AY. Del V by del T is equal to 0, صح? Now come here. Del V by del X, where is V? This is V. What is del V by del X? Is it valid or equal to 0?
0.
It's equal to 0. Come to this component. Del V by del Y, is it valid or equal to 0?
No, it's valid.
It is valid. It's equal minus 0.8. صح ولا ما صح?
Yes.
Come to this one. Basically, we don't have W, but let us look at del V by del Z. Del V by del Z is valid or equal to 0?
0.
Is equal to 0. So basically, AY, the acceleration along the Y component, 0, 0 plus V del V by del Y, 1.5 minus 0.8Y. This is V multiplied by minus 0.8. It is equal to this expression, right? He said at point X equal 2 and Y equal. Therefore, you have an expression for the acceleration, which is equal to this I. If you put I here, plus this J. صح ولا ما صح? If he asks you to calculate the acceleration at X equal 2 and Y equal 3, just substitute X equal 2 and Y equal 3 in these two. He will give you AX, you will get AX as 1.68 meter per second square and AY as 0.72 meter per second square. If you substitute X and Y values. Is there any difficulty here, gentlemen?
Y du by dt 0, the first one.
Y del what?
U by dt.
Del U by del T is equal to 0 and Y del V by del T is equal to 0 يا شباب. He's having a very good question. Now look, this is U يا ابني. اسمك منو انت علي. This is U and this is V. Do you see any time here?
No. We have not.
So the flow is steady يا ابني. The moment the flow is steady, that means the flow doesn't change with time. So del U and del U by del T, del V by del T and del W by del all is equal to 0. Did you get it?
Yes, I got it. Thank you.
Yeah. So the moment he says steady, that means del by del T is equal to 0 for everything. But if, assume I said 0.8 xt here. Do you see what I put here? I put T. The flow becomes unsteady. And then these values are not equal to 0. This is a very good example. This is how the exam will come to you, ya shabab. I cannot move further because it is 10 minutes to 11. I have to stop here, but we will move on. Sketching it, you can see he is sketching it the same way. Okay, right? So we will start this part, inshallah, and we need only 1 hour to finish it off. This chapter, okay? And we'll do the tutorial on Thursday, bi'idhnillah. Make sure, guys, there is a big question in the exam coming from this chapter. It is equal to 6 marks. Attend, please. Thank you very much. Have a good day. Assalamu alaikum.
Thank you, Doctor.